The title of our paper is Origins of Artificial Neural Networks and the Nature of Suitable Applications. This is Lee and David. So introduction, we sought to explain to ourselves what exactly neural networks were and how they first came about. So here are some definitions that I picked up that I thought were very, very accurate. They spoke to us. So neural networks are systems that are deliberately constructed to make use of some organizational principles felt to be used in the human brain. And another name for this is connectionism. And so we read a few papers. I did not read anything by this gentleman, but we started reading with William James. He wrote much about the association of thoughts, and that was he didn't actually know what a neuron was because neurons were discovered by this gentleman, Ramon y Cajal, in 1891. But what James wrote was very prescient, I guess you could say, and some more ideas that came about in the middle of the 20th century were brought about by a Canadian psychologist, Donald Hebb, and he was the first person to make an explicit statement about the modification of synaptic weights. So this was the first definite statement about how learning might take place in the brain. And this other gentleman, Carl Lashley, wrote about the fact that memories and learned behaviors seem to be distributed in the mind. They're not localized. So up to this point in time, people thought that brains were like they described them as, the most advanced technology of the time, which were telephone switchboards. So now we compare them to computers. In fact, I've read authors saying that someday we'll compare computers to minds, but at this point in time, people thought that the mind was like a switchboard, so that you went through a single neuron, a specific point in the brain. So, stimulus elicited a response by a specific route. And this gentleman lesioned the brains of rats and showed that memory, that learned behaviors are actually distributed in the mind to a certain extent. I mean, they're localized somewhat, but for the most part, they do have some distributed nature. And these are the first drawings by Ramon y Cajal. I thought those were pretty interesting. And then we looked at the first models of neurons, of artificial neural networks. The first significant one is Walter Pitts and Warren McCullough. And what they described actually was more like threshold logic units. And so that didn't have a very long shelf life, but it was very important. And then this gentleman is important. Frank Rosenblatt was the first one to talk about learning in the brain. But then this was heavily criticized by Minsky and Pepper because they were the first people to truly investigate the computational limitations of the perceptron. And this is a drawing of the perceptron taken from Minsky's book, which shows what it does. This is the retina, and you have these devices that have individual computations that add together with weights, and then you get an answer to a question. So this is the single perceptron that Minsky used that had one output unit, and it was basically true or false based on a specific question about the image on the retina. And so here's an example of a more elaborate neural network. This is one with multi-layers, and this one's able to answer many more questions than the one we showed you previously. This is just some examples of what the perceptron can evaluate for an object on the retina. But this is a little bit much to explain, so why neural nets? I'll let David take over, and he will explain the applications. Why parallelism, learning ability, inherent contextual information processing, and fault tolerance are important. So.
Okay, so the first case study I came up with, just as kind of an intro to why people would use neural nets. It's kind of an interesting application. There's a lot of papers written on it. It's using sensors connected to neural nets to detect certain varieties of wines, to be able to actually differentiate between real subtle differences in these wines. And nobody knew of any mathematical models to do this, so they actually just used neural nets to learn the differences. So this may not be a very important specific application, but you can use neural nets to model complex behavior that you don't have mathematical models for. Another interesting example is the one-armed robot. It's a robot that you can find videos of online. It's a robot with an arm that is programmed to play around with and see if it can move itself forward. Its objective is to move itself forward. It doesn't know actually how to do this. So it plays around and stumbles upon some kind of motion that moves itself forward a little bit. And after a lot of training, it eventually learns a very good method of moving itself forward. So that's another example. A famous example is Dean Pomerleau wrote a paper on autonomous navigation using image processing fed into neural nets to steer a vehicle. He essentially arranged neural nets like so to pick up on the image of a roadway and figure out how the roadway is changing, basically how the car should steer itself to stay on the roadway. So he found this was a great application for neural nets because the neural nets can learn and they're very adaptable, and they have a very quick calculation time because it's parallel processing. It's processing all these individual pixels parallelly instead of in sequence. So it improves your reaction time, which is important. And one thing he noticed is it's very hard to train these neural nets in this case because you can't just set the car, drive it on the road, and it'll probably crash because these neural nets learn by failing. So he came up with a simulation where he transformed pictures of the roadway in kind of a laboratory environment to train these neural nets, and he got a vehicle that is actually able to drive itself as a result. So what are in the future? Where are neural nets going to go? They can automate knowledge tasks that are difficult to automate today, like medical diagnosis, quality control. They're good at system modeling. They're very good at image processing because of their parallel structure. And they're able to learn about the human brain. We can essentially see what neural nets are good at and what the limitations are and learn more about our own human brains. That's our presentation. Any questions?